Now, hypothesis testing is all about asking specific questions about population parameters. So not estimating them, so to speak, but asking questions about them in light of the data that we have available. So hypothesis is simply a statement about a population parameter. We can distinguish simple and composite hypothesis. So a simple hypothesis ascribes a single value to the parameter, whereas a composite hypothesis is one that states the parameter takes a value in some given set. And when we're testing hypothesis, another important distinction is between complementary hypothesis and hypothesis testing problem. So we define what we call the null hypothesis and the alternative hypothesis. These are being complements to one another. So in hypothesis testing, we'll partition the sample space into two complementary regions, omega subscript naught and omega subscript naught c, the complement of omega naught. And the goal of a hypothesis test is to decide, based on the observed data, which of these is true. Does the parameter lie in omega naught, or does it lie in the complement of omega naught? And this is achieved by first assuming that the null hypothesis holds true, and then we develop a test statistic with a sampling distribution that's known to evaluate whether that is indeed the case, that H naught is true. So a test statistic. We've defined a statistic before. A test statistic is a type of statistic. It's a function of a random variable and therefore has a sampling distribution. It's a statistic that's specifically used to test hypothesis. And the intuition here really is that we're going to construct a test statistic in such a way that if its observed value lies sufficiently far into the tails of its sampling distribution of that statistic, then we're going to conclude that the observed data is sufficiently unlikely under the null hypothesis, and that will allow us to reject the null. That's the way hypothesis testing works in principle. To do this, we're going to define critical and acceptance regions of the sample space. So the subset of the sample space for which the null hypothesis will be rejected, we're going to call the rejection region or critical region. We'll denote that by R. And the complement of the rejection region we're going to call the acceptance region, and we're going to denote that by R superscript C, the complement of the rejection region. Now, because hypothesis testing is always based on a sample, which provides only a limited representation of the population, we can't guarantee it's correct. And we define two types of errors associated with hypothesis testing. The first type of error we call type 1 error. This is when we reject the null hypothesis when it is in fact true. And secondly, we have type 2 error. We accept the null hypothesis when it is in fact false. Now, these types of error are important because we use them to assess a test's ability to provide reliable inference about theta in the hypothesis testing setting. And to do this, we just have to define a few more fundamental elements of hypothesis testing. First, the size and the power of a test. So let R be the critical region for a particular test. The size of the test is equal to the test's type 1 error probability. So size denoted alpha theta is the probability of type 1 error. That is the probability of rejecting the null hypothesis. We say that X is within the critical region when the null hypothesis is in fact true. Now, in setting up the critical region, we're going to have to use some level. A test is said to have significant level alpha if its size is less than or equal to alpha, which must be less than or equal to 1. Okay, so significance level of alpha if the size of the test is less than or equal to the value that we use, and I'll show you in a minute what values are often chosen. Next, the power of a test. The power of a test, 1 minus beta open brackets theta, is equal to the probability of correctly rejecting the null hypothesis. So the power of a test is equal to 1 minus the probability of type 2 error. That is the probability of rejecting the null hypothesis when H1, when the alternative hypothesis is in fact true. And then the final element we want to introduce is what's called a p-value. A p-value is defined to be the probability under the null that the test statistic takes a value at least as extreme as the one that we end up observing. Small values of p, small p values, give evidence that H1 is true, that the alternative hypothesis is true. So let's just have a look at how these elements fit together. The p-value, therefore, is the probability of obtaining a test result, test statistic, at least as extreme as the result that we actually observe, under the assumption that the null is correct. The good thing about a p-value is that it allows us to evaluate a test not just on a dichotomous scale of accept the null or reject it, but on a continuous scale, because it's a probability and therefore falls in that region between 0 and 1. Now, we talked about significance levels for a test, and we have to set significance, should be fixed at some small level. And typically, the values of alpha that are used to set the test and define the critical region are 0.01, 0.05, or 0.10. And as these are increasing, the critical size of the critical region is, of course, changing. So the diagram below represents the sampling distribution of a two-sided test. We'll define this formally later, using a significance level of 0.05. And that significance level of 0.05 says 95% of observations fall in this region. Only 5% of all observations fall in these two tails, and that's our rejection region for the test. Alpha over 2 on this side, which amounts to 0.25 probability of falling here. Alpha over 2 on this side, which amounts to 0.025 probability of falling here. And that's our rejection regions there for the test. So that's in principle the elements of hypothesis testing and how they fit together. We'll now look at some general methods and use some examples which hopefully will make this concrete.